Hello and welcome to Lecture 13. Here we're going to continue into Chapter 5, discussing sections 5.3 and 5.5. The topics here are going to be potential energy, specifically gravitational potential energy and elastic potential energy, which is why I have this section split up because I felt they naturally go together. All right, so let's take a look at our key terms. So we're going to start off by defining energy. If you watched the last lecture, you saw that I already defined energy, but I'm going to say it again just to kind of make sure we're clear on the idea. All right, so energy is a physical quantity that is capable of doing work. Okay, again, tying it back to that basic idea of work being force multiplied by distance, or at least the component of force that's parallel to that distance. Okay, and we have seen kinetic energy already, but another type of energy is potential energy. Okay, and that's what we're going to discuss here. All right, so what is potential energy? It's simply stored energy. That's the useful way of thinking of it. Potential energy can transform to kinetic energy and or do work. Okay? There are two types of mechanical potential energy. The term mechanical is going to come up again. Effectively, mechanical is basically anything that's driven by gravity. There are some exceptions. You can have some external force other than gravity. In practical purposes, mechanical is heights and springs. All right, so it's basically like ramps, moving up and down in the vertical direction, and springs. Everything that's not mechanical is heat in this class. In physics in general, non-mechanical forms of energy or non-mechanical physics in general could be electromagnetic or nuclear, okay? As well as quantum. All right, but for us, the two types of the two types of mechanical potential energy are gravitational and elastic. Those are the only two types we care about. Okay? Now, since we're going to be talking about elastic potential energy, that means we're going to be talking about springs, which means we need to define something called Hooke's law, which is the law of ideal springs. And when you see that word ideal, you basically read that as like perfect springs where they're massless, they don't have they don't lose any energy to heat, for example, they work perfectly, okay? So those are ideal springs, all right? And Hooke's law applies to them. It states that there is a direct proportionality between applied force to that spring and the spring length change. Okay? So, you double the force, you double the change in length of that spring. That's what it's saying, a direct proportionality. And the spring constant is, first of all, the one value that defines the spring. So any particular spring has a spring constant. It's individual to that spring. And it's the only thing you need to know about that spring as long as it's an ideal spring. Because again, springs are assumed to not have mass. So literally the one thing that defines them is their spring constant. Okay? And what it is it's the proportionality from Hooke's law. Okay? Because if there's a direct proportionality, then there has to be something called a proportionality constant, and that's what the spring force is. Okay? Hopefully that makes sense, but I'll reiterate it and kind of explain it some more. Okay? The units of the spring constant are newtons per meter. And here's the further explanation. So when you have a direct proportionality, that's the same as saying linear. So essentially, if this is the external force acting on a spring, and then this is the change in length of that spring, x, right? So force measured in newtons, change in length of the spring measured in meters, and then so here's the spring getting longer, right? So direct proportionality, linear length change of the spring. The slope is the spring constant. And we represent the spring constant by the letter k, lowercase k. Okay, not that you can tell so much of k's, right? But that's the spring constant. It's the slope of applied force to the spring over the change in length of the spring, rise of a run, okay? That is K, graphically, okay? And, so that's the thing, another thing about ideal springs is we assume that they stay perfectly linear. The springs never wear out, they don't end up having some permanent bending to them, right? So perfect linear relationship here. Okay, so now let's back to general ideas of potential energy. Let's look at our key formulas. All right? So first of all, we have PEG, that's gravitational potential energy on Earth's surface. I make a deal about calling it on Earth's surface, not to be overly technical, but it's, especially if we're talking about gravitational potential energy, a lot of times that does apply to things that are far away from Earth, in which case it would be a very different formula. So I think it's important in this case to specify that really we are talking about, things in the first, few hundred meters above Earth's surface. Okay. But anyway, that's going to be all the problems. We're not going to see anything that's going to break that rule. And the form of gravitational potential energy is mgy, simply that. Mass times gravity times y, which represents height. Now, y is measured relative to whatever you call your 0 point. So that means the gravitational potential energy is arbitrary to a particular system of coordinates. So if I call the floor y, then my gravitational potential energy relative to the floor is however high I am above the floor. But then if I acknowledge that the floor is actually the second floor of a building, so then if instead I call y equals 0 the ground, now I have a different amount of potential energy relative to the ground than I do to the floor, right? And so in that respect, it's arbitrary. And gravitational potential energy can also be negative because you can be below the floor, right? You could go underground even, okay? And so as long as you're not going, thousands of meters and significantly changing your gravitational acceleration, then it's always going to be mgy. It can be positive or negative, and it's an arbitrary choice. It's just a way to find out what that potential energy can do. Perhaps that potential energy can do work, right? Perhaps that gravitational potential energy can create kinetic energy, right? But it's always based on the coordinate system. Okay, I think that makes sense. And notice I am using PE here. That's because we generally use P for power. So I think it's important to call potential energy PE. Okay? And the G just denotes gravity. That wasn't obvious. Now here's an interesting thing. The change in gravitational potential energy is equal to the negative of the work done by gravity. Okay? So why is that? Well, I mean, because, it kind of seems strange, right? Wait. So if I'm changing potential energy, it's why the negative? Well, it's actually quite logical. Because think about it. If I'm going up, that's a positive change in gravitational potential energy because my y has gotten bigger, okay? Because that would be, so here my delta PEG would be mg y final minus y initial, right? So positive means my y final is bigger than my y initial. Well, if I've gone up, that means that gravity has done negative work. Why? Because gravity would be acting anti-parallel. I'd have a cosine of negative 180, or cosine of 180, which would give me a negative 1 in the definition of work formula. The fact that it would be, mg cosine of phi, right? And if I'm moving against the direction of gravity, then gravity is doing negative work. On the other hand, if I'm losing potential energy, that means I'm falling. Well, that's when gravity does positive work, because then the displacement is parallel to the gravitational force vector, right? Okay, refer to the last lecture notes to make sure that makes sense. Okay? All right, so, interesting idea, should make sense, and important. Okay? So that's enough about gravity. The rest of these are all about springs. Okay, so the first one is Hooke's law. Okay, here is that direct proportionality. Okay, K is the spring constant. F external is the external force on the spring. Maybe that's from hanging a mass on the spring. Maybe it's just from pulling on the spring, right? But some external force acting on the spring. Okay, then we also have this idea that we have the Fs. Okay, this is the reaction force of the spring. So this is the spring force. So Fs is equal to negative F external by Newton's third law. Okay? Because the idea there, if you pull on the spring, then the spring pulls back. Sometimes the spring force, F sub s, is called the restoring force because it's the spring wanting to return to its original length, its unstretched or uncompressed length. Okay? And then finally, we have elastic potential energy. All right? So elastic potential energy, 1/2 kx squared. K is the spring constant. X is just the change in length of the spring. This is how much energy is stored in a stretched or compressed spring. All right, let's do some examples. All right, so there's only two types. Problems that involve gravitational potential energy and work, and problems that involve elastic potential energy and Hooke's law. That's it, right? We just kind of have the two types here. It's a pretty simple lecture. We'll kind of get into the more kind of intricate problems as we move into the end of the chapter. Okay, right now we're just laying down the basics. All right, so example 1. An elevator with mass 1,200 kilograms ascends a height of 374 meters while going between floors in a building. How much potential energy does the elevator gain, and how much work is done by gravity? All right, well, okay, so the change in potential energy is just mgh. Here I'm just kind of writing it as the final potential energy because I'm assuming that the initial potential energy is 0. So basically like h naught is 0. So I kind of feel like that makes sense. So I'm just going to write as mgh. So it says 1,200 times gravity times 374 meters. Okay, the final height. So that's how much gravitational potential energy our elevator gains. 4.4 million joules. Quite a bit because it's pretty tall and it's a pretty massive object, right? Big numbers here. Okay. Now, this, as far as the work done by gravity, well, the work done by gravity is just equal to the negative of the change in potential energy, so it's just going to be negative 4.4 million joules, okay? Because we worked against gravity. That means that's how much energy it would take to gain that much potential energy. We have to put that energy in somehow, from maybe some, from like, running a motor, right? An electric motor, a gas-powered motor, whatever it may be. This is the energy input because we have to work against gravity, right? Let alone probably working against some friction, But that's the idea, right? Gravity does negative work. Okay? And this is consistent, as I said before, with the idea that the work of gravity is the force of gravity times height times cosine of 180, right? Because they're opposite directions. The force of gravity is down, that's the vector, and the displacement is up. So the angle between them is 180. Cosine of 180 is negative 1. That's why gravity does negative work. Okay, I think I made the point enough, right? So example 2. A 1.15 kilogram ball is rolled down a hill that has a length of 211 meters, pretty long hill, and a steady slope of 11 degrees. How much potential energy does the ball lose in this descent, and how much work is done by gravity during the descent? Okay, so here's the ball rolling downhill, all right? So what we want to do is we want to take a look at the geometry here and notice that sine theta is opposite over adjacent, or opposite over hypotenuse, so it's h over L. That means that h is just L sine theta, all right? That's going to be the height. That would be the height that shows up in the formula mgh. All right, therefore the change in potential energy of gravity here is PE final minus PE initial. Here I'm writing it out as a change, just to be clear. All right, and then PE final is once it gets down to the bottom, it has no leftover gravitational potential energy, because here we're calling this y equals 0. That's the end of potential energy. That's as low as you can go in this particular system. And then minus the initial potential energy, mgh, all right? So that means we'd have a negative 1.15 times 9.8 times 211 times sine of 11 degrees, right? Because this together is our h, okay? And when we plug in all the numbers, we have negative 453 joules, okay? That's how much the potential energy changed. We could also say we lost 453 joules, but the change was negative 453, okay? Well, if the potential energy is going down, that means gravity must be doing positive work, right? And indeed, that's what we see. Gravity did positive work equal to 453 joules, okay? Okay. All right, so that's kind of the flip side of the elevator, going down instead of going up. Now let's consider a spring. A spring is hung vertically and a 100-gram weight is attached to it. Okay, let's take a look at the picture here. All right, there we go. All right, there's the weight. All right. It is found that the weight extends the length of the spring by 5 centimeters. That's this stretch here. Okay, and by the way, the original length of the spring, I call that the equilibrium. That's a point that becomes, or that's a term that becomes more important when we talk about oscillations. But here, equilibrium is also just kind of the original length of the spring, okay? Okay, so anyway, so it stretches by 5 centimeters from the original length. And then question A, what is the spring constant of this spring? Okay, well, we can use that information, that 5 centimeter stretch, and the fact that we added a 100-gram weight to find it. So I'm just going to say F external is just 100 grams times gravity. F external equals kx, right, by Hooke's law. So that means I can just solve for k, F external divided by x, right? I know my x, my stretch, was 5 centimeters. So that means that k is 19.6 newtons per meter. That is the spring constant of this particular spring, okay? All right. So then, in part B, I say that same spring is then stretched by hand an additional 15 centimeters. What is the total stored potential energy in the spring? Okay, well now I'm going to have 1/2 k, the k I found in part A, and then x total. X total is that additional 15 plus the initial 5, right? Because that 5 was storing potential energy, right? We're just even adding to it by hand. So that means that our change in length is 20 centimeters. Okay, we make sure to square it because the formula is 1/2 kx squared, okay? And by the way, this derivation of the formula comes from calculus, so we're not going to cover it here. But there's the formula. Plug in the numbers that we know, and we find out that the stored energy is 0.392 joules, okay? That's how much stored energy there is in the spring. Now here's an interesting question. What is the total change in the weight's gravitational potential energy from the moment it's attached, right? Will it be equal? Is this a thing like if I gained a certain amount of elastic potential energy, then did I lose an equal amount of gravitational potential energy? And I'm definitely going to be losing gravitational potential energy because I'm going to be going down, right? And every time you go down, you lose gravitational potential energy. That part is not arbitrary. You have to lose gravitational potential energy because the force of gravity only acts in one direction, okay? So anyway, so let's see. Well, I just plug in my numbers, all right? So my PE final is going to be 0 because I'm going to call y equals 0 the bottom. So now, as far as the coordinates here, right? So I'm kind of using x for the spring. I'm calling x equals 0 the initial length of the spring. I'm using a separate coordinate system for height. Why not, right? I mean, I can consider them separately. And there I'm going to set my 0 point as the bottom. That's totally allowed, okay? Now, calling it x when it's kind of vertical motion might seem counterintuitive, but the Hooke's law is written as x. I figured I might as well to distinguish it from using y for gravitational potential energy. Okay? Anyway, so then we got, so then once it gets all the way stretched to the bottom, I'm calling that 0. That's my choice, right? As long as you're consistent, it's fine. And then my mgx total is the initial potential energy. That's when it was up here, right, when the box is at the top. Okay, so that means my change in gravitational potential energy is negative 0.196 joules. So the box lost 0.196 joules of gravitational potential energy. But they're not equal to each other, right? They're not equal. So why is that? Why is it that I can gain more elastic potential energy than I lost gravitational potential energy? That's kind of interesting, right? Well, keep that in mind. We're going to talk about that in the next lecture, okay? All right, because that energy has to go somewhere. All right, it's a cool idea. Okay, so a couple more. All right, so this one's quite repetitive with the last one. I think I was kind of going to go somewhere else with it, and I was writing the lecture, but we'll just kind of run through it as extra practice. All right, in this case, we're instead of it hanging something from a spring, we're putting it on top of a spring. So I guess at least the purpose of this example is to show that if you're placing an object on top of a spring and compressing it, there's nothing fundamentally different than hanging an object from a spring and stretching it. Okay, so here from Hooke's law, we have the force of gravity equals kx. All right, this time we actually are given k, and we're just asked to solve for x in part 1. What distance does the spring compress? So then our external force is just gravity, so mass times g, right? Gravitational acceleration divided by the spring force. All right, and this ends up being a really big spring force and not a very large weight. So our compression is definitely not to scale in the picture. So unless this is a very small spring, because it ends up being only 4.2 times 10 to the negative 4 meters, or about half a millimeter, less than half a millimeter, right? So tiny compression. It's a very stiff spring. And then I ask, how much work does gravity do during this compression? Well, okay, so then it's going to have 0.227 kilograms times 4.2 times 10 to the negative 4 meters, right? Because we found that from part A. So we find that gravity did a tiny bit of energy, or did a tiny bit of work, 9.5 times 10 to the negative 5 joules. Positive because it went down in the same direction, right? So it's cosine of 0 degrees, okay? So, which is a 1. But yeah, anyway, even smaller than the amount of, actually we didn't calculate the elastic potential energy, but even smaller than the distance, right? Tiny value, okay? And then finally in part C, what was the change in gravitational potential energy? And it ends up just being the negative of the work done by gravity. Of course it is, right? We already saw that. Okay. All right, so moving right along, example 5, you push on the spring with a force of 256.5 newtons and find that the spring has a compressed distance of 13.4 millimeters. What is the spring constant, and how much elastic potential energy did you store in that spring if you then compress it 3 centimeters? Okay, so again, very similar, but we'll run through it. So we're going to use Hooke's law. We're going to go ahead and solve for k because we weren't given it, but we're given the information to find it. In other words, external force and a particular displacement that corresponded to that external force. So there we go. It's a rather large spring constant, 19,100 newtons per meter, or 1.91 times 10 to the 4, right? That's where the 19,000 comes from. All right, and then if we want to find out how much stored elastic energy there is, we're just going to use our formula, 1/2 kx squared, plug in our k. We'll plug in 3 centimeters because we're compressing it more than the initial distance that we used to find k. And we find out when it's compressed 3 centimeters, this particular spring stores 8.61 joules. All right, not a lot of energy, but it wasn't a very large compression, was it? All right, so here's an interesting one to wrap things up. What happens if we put springs in parallel and series? All right, well, we can kind of consider Newton's second law and kind of set it, be just consistent with the idea of forces and distances and figure that out, and then answer the questions, which is how much elastic potential energy is stored when the springs are parallel to each other, and how much elastic potential energy is stored when the springs are in series with each other. And actually, just come to think of it, I actually didn't solve for the stored energy. I just solved for the displacement. So I was solving for a different version of this problem. So I'll go ahead and just finish it up with the solving for the displacements, and I'll leave that last step. I'll have written out the last step, but you're not going to see it in the video. So go check out the notes if you want to see the final step where I take the x that I solved for and find the 1/2 kx squared. All right. So the key idea with both of these, however, the interesting part, besides the last step, is this idea of an effective spring constant. So I want to find the effective spring constant of the 2 parallel springs, right? Starting at part A, all right? and x must be the same for both springs. So in other words, I can't stretch the one on the left more than the one on the right, because then it'd be lopsided. And that's impossible. They have to stretch the same amount. Okay? Now if they had different spring constants, then they could have different forces in them. But what they have to share is stretch. Okay? So that means that F net is kx plus kx minus mg, which means that 2k times x minus mg is the net force. Well, that just tells us that the effective spring constant when they're side by side is just 2k. Putting them side by side just doubles the spring constant. It's like having a spring that's twice as stiff. Okay? So then if I want to then use Hooke's law to solve for the stretch of the springs, it would just be my external force of mg divided by my effective spring constant, which is just twice what either of them is individually. So that gives me a stretch of 1.5 centimeters. Okay? So that's the idea for the parallel springs, the side by side. But what about when they're in series, which is to say in a row? Well, that's a different story. Okay? When they're in series, again, we want to find this idea of an effective spring constant, right? A total spring constant that defines the system. Okay? And this time, the external force must be the same for both springs. Okay? So here they could experience different forces, right? And they don't because they're the same spring constant, but they could if they had different values of k. Okay? But we just add up the k's to get the effective spring constant because they have to share the same stretch. Here, however, they have to share the same force due to Newton's third law. Okay? But they could stretch different amounts. If this spring was, say, less stiff than the bottom spring, then the top spring would stretch more, the bottom spring would stretch a little bit less, but they would both experience the same force. Okay? Furthermore, the total stretch of them has to add up. So there has to be some x total, which is the sum of their individual stretches. Here, there's no subscript of 1 and 2 because they're just both the same, so I'm just calling them x and x. Okay, that's the stretch at the top and the bottom, we could say. Okay? So then what we can do is we can say, okay, well, x total is F divided by K effective, because that's for the whole system. Meanwhile, x, for either the top or the bottom is F over K, and then the other one is just, again, F over K, right? And all those forces have to be the same, so they cancel out. So then we can go ahead and solve for K effective, all right? I'm just going to find a common denominator here, which is just K times K, and then I would have K plus K in the numerator. So 1 over K effective would be K plus K over K times K. Okay, just a little bit of algebra there. And then I can just take the reciprocal of both sides, effectively just raising both sides to the power of -1, if you've seen that. All right, so then K effective would then be, by swapping it, then I have a K squared, because K times K is just K squared, and then my K plus K is 2K, which means that one of my K's cancel, and then I find that my K effective is 1/2 K. Ah, that's interesting. So putting them in series actually reduces their effective spring constant. When they're in parallel, it was like having a spring that was twice as stiff. When they're in series, when they're in row like this, it's like having a spring that's half as stiff. So it actually makes them weaker when you put them in series. All right? So then, if we want to find the stretch, well, it's the external force mg divided by that K effective. So then it's 3.5 times 9.8 meters per second squared over 1/2 of the K of the individual springs, which was 1,140 newtons per meter. And so then we have a stretch of 6.02 centimeters. The stretch is 4 times as long. All right? So putting them in series means you get 4 times as much stretch. Quite a dramatic difference. And then if you were to go on and find the actual stored energy, well, stored energy, is 1/2 kx squared. Well, if you think about it, your k for this one is going to be twice as big, and then your stretch is going to be half as big, and then you're squaring the case where it's half as big, right? And over here, I mean, so it's kind of interesting to think about it, right? So, but you know what? I'll just gonna leave that for you, right? I'm just gonna I'll leave these as the final values, and if you want to answer the question of finding elastic potential energy, then just remember that stored elastic potential energy is just going to be taking 1/2 K effective, depending for either A or B, times X squared. Okay, and you can see how it differs. Okay, because I think it's interesting, and I'll leave it as something to follow up with. Okay, well that is it for lecture 13. I hope this was a good kind of brief and hopefully fairly simple introduction to the idea of potential energy in these two forms. Okay, so please check out future videos for Chapter 5, where we're going to get into energy conservation. Thank you so much for watching.